Today we will start chapter 4. Chapter 4 is about exponential functions and their inverse functions, the logarithmic function. Roughly speaking, we have here, in fact, 4 sections, not 5, as they is showing. 4.2, it is just about one definition. What is the natural exponential function? It is just special case from 4.1. In 4.3, we'll study the logarithmic functions. In 4.4, we will study the laws of logarithms. By the way, we will study also the laws of exponents in 4.1. Indeed, you already studied this concept before. The laws of exponents, they are in MATH002, chapter P, section P3. In the last section, we will study exponential and logarithmic equations, how to solve this. Let's start with 4.1. The exponential function. What is the exponential functions and how they look like, how the graph of them is. So I'll assume that you don't know anything about exponential functions, and this is how you should deal with any new function that you don't know. I think, ya shabab, you know from where the name is coming. Exponential is coming from where? Exponent. And you know what we mean by exponent. When you have, for instance, when you have a to the power m, here, what is the base? What is the exponent? The base is a, the exponent is, there is another name for the exponent. What is it? Power. So when you have x to the power 2, the base is x, the power is 2. Or the exponent is 2. We give, if you have a function like this is well-known function. In general, when you have x to the power n, x to the power n here is any real number. We give a specific name for such kind of functions. What we call them? Do you remember from MATH001? Power. We call them power functions. In fact, it is not that difference, but we just need to distinguish between them. We are all here men in this class, but we have different names, just to be easy to know this from that, to distinguish between them. So now, as you can see here, x to the power 2, x squared, it is well-known function. You know how the graph of this function, what are the properties of this function. And for x, it is always carrying the powers, 2 on its shoulder. Now, it is time for 2 to be to the power x. The power now, the variable is in the exponent, not in the base. And this kind of functions, it is a function, by the way. It will define a function, and we will see why it will define a function, because for each x, there will be only one y. So we will have for each input only one output, and in this case, it will be a function. This function, we will call it exponential function, to distinguish between it and between the power functions. So it is clear what we mean by the exponential function. It is about when you have a constant, a fixed number, well-known number, you know what is it? It is not a variable, and it is to the power what? X. The variable of the function is here. So when you have such function like this, we call it exponential function with base a. Look at it. The exponential function with base a is defined for all real numbers x. What does that mean?
We can plug in any number we want.
Right, you are right, totally right. So mathematically, what does that mean? Yeah, salam alaikum. Yes, the domain of this function is all the real numbers from negative infinity to infinity. The domain of this function is all the real numbers. Excellent. So it is defined by this one, where a is strictly positive, strictly greater than 0, and not 1. Look at these some examples. 2 to the power x. What is the base? 2. 3 to the power x. The base is 3. 10 to the power x is 10. No one asked about this, Shabab. Why you are not wondering why it cannot be 1, why it cannot be 0, why it cannot be negative. Let's start with the first one. Why it cannot be 1? Yes.
1 is constant.
If it was 1, it will be a constant function. You are totally right. It is here. So what will happen if it is 1? It will be 1 to the power x, it will be 1, it will be a constant function. It will not be 1 to 1, so it has no inverse. Its graph will be just a horizontal line. So it is completely different from the exponential function. It is not exponential function. Okay, what about 0? Why a cannot be 0? Please, another one. Yes.
Because the y will be always 1.
No, this is in the case of 1. But in the case of 0, this is something else. In fact, dividing the exponents when the base is 0, it is kind of risky. You have to be careful with that. So it will be 0 to the power x. This is the function. So is it always 0 or is it always 1? You said no. It is not. For example, 0 to the power 2, 0 times 0, which is 0. Just simply, if you can think about it like that. And when you have 0 to the power 0, this is another issue. When you have what? Where is the problem? Will be where? Yes.
When the exponent is 0.
When the exponent is 0, in fact, as exact value, it can be considered as 0, but it is in fact indeterminate. You will see that in Math 101. When x approach 0, not exactly 0. The problem will be more clear when you have what? Negative. Look, for example, 0 to the power negative 1. What will happen in this case? It will be 1 over 0, which is what? Undefined. So it will not be defined for all real what? If the base is 0, it will not be defined for all real numbers. It will be defined at some, undefined at others. So it will not be an exponential function. Similarly, for the negative, what about if it is negative? Think about, for example, negative 1. What will happen if it is negative 1 to the power x? Yes.
If the x is odd, the behavior will change if it is even.
If you are just talking about integers, yes. If we just think about integers, if it is positive, if it is all even, it will be what? 1 if x is even what? Even integer. And it will be negative 1 if x is what? Odd. But we are talking about real numbers. Not all the real numbers, just odd and even. So where is the problem will be? Yes. It might be undefined at some values of x, like what? Like a half. Negative 1 to the power half is the square root of what? Negative 1. This is the imaginary unit. This is I. It is not a real number, and it should be defined for all real numbers. So this is why you should realize we exclude all the values. And from now and on, by the way, in this section, in the next sections, when we define the logarithmic functions, the base cannot be 0 or negative. It is strictly greater than 0 and not 1. Okay? Excellent. So, this is another amazing fact about this function. A to the power x is always positive. Why? Whatever x is, a to the power x is always greater than 0. Why? Yes, please.
Because the exponent doesn't change the sign.
Why? Again, yes.
Because a is bigger than.
Yes, exactly. Because a itself is greater than 0. So when you have something positive, whatever the power that you will raise to, the result will be always positive. So when a is greater than 0, a to the power any power will be greater than 0. Let's take an example. Let me give you an example about that. Let's take 2. Let's take a for an instant. A equals to 2. Now, raise it to any power you want. Give me any power you want. Positive. Think about positive. 2 to the power 3. Good. So you can think about any another positive value. It will be positive. Now think about the 0 itself. 2 to the power 0. 1. Give me a negative number. 2 to the power what? Negative 2, for example. 2 to the power negative 2? 1 over 4. So whatever x is, positive or negative or 0, the a to the power x will be always what? Positive, greater than 0. What we conclude when we talk about functions, so what does that mean? Yes.
That is the range.
The range, the output is always positive. The range is what?
Bigger than 0.
From 0 to infinity. So the input here is in a real number for these kind of functions. The output is only and strictly the positive numbers. Great. This is an example. F of x equals 2 to the power x. What is f at negative 1?
half.
A half. Just substitute by x by -1. F at 3 will be what? 8. F at 5/2. Just you will raise 2 to the power 5/2. And to simplify it, you will take 2 to the power 5, which is 32. Under the square root, it will be square root of 32. Square root of 32 is 60 multiplied by 4. So it is 4 square root of, to simplify as much as possible. Okay. Now we need to, before going further, you need to recall the laws of exponents. And this is, again, this is, I believe it is section B3 in chapter B. Am I right? I think it is B3 in chapter P in MATH001. Do you need to go over them one by one, or it is clear? I think they should be clear. And if they are not, please revise them. So let me add some additional properties or some additional laws for the exponents. You need these, especially in sections 4.4 and 4.5, I think, mostly in 4.5. Again, when we talk about the base here, a, it is always greater than 0 and not 1. So now here, when you have a to the power b equals to a to the power c, when you have two exponential expressions equals to each other with the same base, so also you have the same exponents. And it is f and only f, by the way. If you have a to the power b equals to a to the power c, this implies that b equals to c. Also, if you have b equals to c, this implies that a to the power b equals to a to the power c. Let's go to the second one, and this is what is interesting, in fact. When you have, let's say, when you have n less than m, is a to the power m n always less than a to the power m?
Not necessarily.
Not necessarily. So when it will be true? If a is greater than 1, this is true. What about if a is less than 1? And when we say less than 1, it means by default greater than what? Greater than 0, because it cannot be less than 0. So if a is between 0 and 1, and n is less than m, what will happen to a to the power n and a to the power m? Are they still less than? Unfortunately, they will, the sign of the inequality will be reversed. It will be greater than. Indeed, this is an increasing function. This is decreasing function. We will see that later. Let's take an example. It will be more clear for you, Shabab, if you had an example about this. This fact is mentioned here. Let's take, for example, 2 is less than 3, right? Now, think about a to be 2. So now you will have 2 to the power 2 and 2 to the power 3. Is it valid? 2 to the power 2 is 4. 2 to the power 3 is what? So 4 is less than 8. So this is less than this. What about now if a is a half? Less than 1. 2 is less than 3. Is a half to the power 2 less than a half to the power 3rd? In fact, it is bigger, because this is 1/4 and this is 1/what? 1/8. It is bigger. And this is what is mentioned here. Okay. It is time for you, if you realize these facts and these laws of exponents and these properties, you can solve the first recitation exercise. It is not about MATH002 at all. It is about MATH001, how you can play with powers, with exponents. Please try to solve this recitation exercise. If you can solve it, this is so nice. If you couldn't, it is not a problem, because we're still practicing, we're still learning. During that, I will take the attendance, but I need to pause the recording first. So the answer is C, 9. So how did you solve it?
4 to the power x plus 2.
So you worked on this one. Sorry, you worked on this one until it becomes like this, or you worked on this one until it becomes like this, or what you did exactly?
I worked from the given y equal 4 to 1 x plus 2,
Mhm.
5 to till I reach y equal.
You can do that. This is one way, Shabab. So you can work on this one until it becomes like this, or work on this one until it becomes like this. It is about what, in fact? It is about the base here. What is the base here? And the base here is what? What is the relationship between 4.5? Who can give me 4.5? How they can be equal to each other if we did what? 4 is what? 4 to the power what? Equals to a half. No. Be careful. Negative half. 4 to the power negative half is a half. Are you okay with that? Is it clear? So again, a half to the power what? Equals 4. Negative 2. So you can use this fact here until it becomes like this. Or use this fact here. Again, I'm doing the opposite. You can use this fact here to becomes like this. Or use a half, again, a half here. A half, it is this. So you can, let me show you. But I have a better way. So here you can say this is k multiplied by 4 to the power negative a half, all to the power bx plus c. And then it will be k 4 to the power negative bx plus c. And you just compare it with what? With what you have there here. You will compare it with, by the way, this is 4 to the power x multiplied by 4 to the power 2. Is that right? So I will do it for you, but just I'm sketching another ideas. Now here, if you work here, you can do what? You can say this is 4 to the power x multiplied by 4 to the power 2 minus 5. And then 4, replace 4 by what? By a half to the power negative 2, multiplied by 16. And you will compare it with what you have here. But the best way is to work on both. So don't go with the 4 up to until it becomes half, and don't work on a half until it becomes 4. You can bring them together to the middle. In fact, if you think about it, you have here 4 to the power x plus 2 minus 5. You need it to be the same as what? As k to the power a half bx plus c. So this one is written as this one. Now you need to know just what is k, what is b, what is c that satisfy this. Okay? So what we will do, we will work on them at the same time. And I believe that this is the best way. Of course, you can use what I told you before. So this will be 4 to the power x multiplied by what? 4 to the power 2 minus 5, right? And this will be k to the power 2 to the power negative 1, all to the power bx plus c. And this is 4 to the power 2, what is it? 16 multiplied by 4 to the power x. 4 to the power x is what? It is 2 to the power 2, all to the power x minus 5 equals to k to the power 2 minus bx plus c. Are you with me? Just I wrote a half as a 2 to the power negative 1 and 4 as 2 to the power 2. So now it should be clear. Now this is 16, 2 to the power what? 2x minus 5 equals to k multiplied by 2 to the power negative bx plus c. Now when these two expressions will be exactly the same, identical. If what? If 16 is what? K, and you have here 2, the same base, 2 to the power x equals to negative, 2x equals to negative bx. In fact, you have xx here. It is about 2 equals to negative b. And then what? Finally, negative 5 equals to what? To c. From here, we conclude that k is 16, b is negative 2 multiplied both sides by negative, and c is negative 5. What is the sum of them? The sum of them is 9. He's asking about k plus b plus c. If you didn't solve this one, for sure you will be able to solve this one. This is the second recitation exercise, and you can solve it. Believe it or not, you can solve it. Even we didn't start real 4.1, 4.2 for real, you can solve this exercise. Find the intersection points of the graphs of y equals 3rd to the power 2x plus 5 and y equals 27. You know this function. What is this function? A horizontal line, okay? And this is what? Exponential. This is a horizontal line, and this is the exponential. Is it increasing or decreasing? We will see that later. How its graph looks like, we will see also that later. You don't need the graph. But we will see later that these graphs are always increasing or always decreasing. So they will have only one intersection point. He's asking about the intersection points. They might be more than one point. The concept of finding the intersection points. Are you aware about this? How to find the intersection points between two graphs? You can do it geometrically or algebraically. Geometrically, if this is the graph of the function y equals f of x, and there is another function, let's say y equals g of x. They are totally different functions, but at the intersection points, they are the same. Here, at this point, they are identical. So at this point, what happens? It is a point in the plane. It is x and y. At this point, x is the same here and here. Y is the same here and here. So how to find this point? The point of intersection. Yes.
X equals -4.
No, I'm asking about this in general. In general, if you want to find the intersection points of two graphs, what you will do? I'm talking about the graphs of functions.
We equate the two.
Equate them. You will both them equals to each other. This y equals to this y. So f of x equals to g of x. You will solve it and find what? X. Then you will go substitute in g or in f to find what is y. And they should be the same. So this is the idea. Please apply it for this exercise. Did you finish? What is?
-4 and 27.
Right, you're right. What about you?
Yeah, the same.
This is why I said I expect that most of you will solve this yesterday. It is not difficult. It is just about the laws of exponents. Are you aware about the laws of exponents? How to play with exponents? So what you will do here, this y should be the same as this y. So you will just solve this equation. Again, we will do that, inshallah, in 4.5. This kind of equations is called exponential equations. How to solve it? You will play with third. What is third? It is 3 to the power -1. So it will be negative x and -5 equals to 3 to the power 3. Is that right? You will keep in mind that you should have the same base. If you have the same base, you can work with it. Do we have the same base now? 3, 3, the same base. So two expressions with the same base equal to each other. This means what? The exponents are the same. In fact, we will see that in 4.5, we will take log 3 for both sides, the logarithm, the third logarithm for both sides. But it is not, it is easier than that. Look how it is now. Just we use the fact that if you have a to the power b equals to a to the power c, this implies that b equals to c. Now, this is negative x equals to what? 8, x equals to -4. This is x. How to find y? You can go and substitute here, but it is much easier. It is given here. So y is what? 27. If you even substitute there, it will be 27 because we are at the intersection point. Excellent. Let's continue. Now, it is natural to ask yourself how these graphs or how these functions look like. The exponential function, how they look like. I'll assume again that you didn't see them before. You have no idea about them. How you will sketch the graph of a function that you have no idea about, that you didn't see before? Yes.
Sketch 5 points and
Yes, you're right. There is a name for this method. Yes. Plotting points. Here it is. It is called plotting points. So you will just plot some points and then connect them. This will give you the graph. Now, how to get these points? As you said, you need to choose or to make what is called table of values. So you will select some values for the input x, and you will see what are the outputs y. Now, you have to be smart when you choose the x values. Of course, it is natural to think about 0, 1, 2, 3, -1, -2. So look here, we have here 3 to the power x. When x is 0, what you have?
1.
When x is 1, 3 to the power 1. 3 to the power 2, 3 to the power 3. Now 3 to the power -1, third, 3 to the power -2, 1 over 9, 3 to the power negative, it is 1 over 27. Now let's go and plot these points. Let's plot them. Now 0 and 1, this is 0 and this is 1. 1 and what? 1 and 3, let's say here. 2 and what? 2 and 9, it will be here. and so on. Let's go back here to the negative direction. When x is -1, what is y? Third, like here. When it is -2, 1/9, it will be very small here. Now we can connect these 2 points that we have plotted, and when we connect them, we will get this graph. Now we know how they looks like, how this function, specific function looks like. Excellent. Let's now go and sketch the graph of the another function, third to the power x. Again, we don't know what will happen here. Here, by the way, the base is greater than 1. What will happen if the base is less than 1? Again, I'm assuming that we have no idea about it. How to do that? With the same idea, you will plot the points by making some table of values. Now, again, we will apply the same idea. Let's apply it now. You have 0. When x is 0, what will be third to the power 0? It will be 1. What is third to the power 1? Third. What is third to the power 2? 1/9. And third to the power 3? 1/27. Look here. Third to the power -1? 3. Third to the power -2? 9. And you can notice something amazing. What were here, now they are here. And what was here? It is here. Okay. Now let's plot the points. Let's now plot these points. 0 and what? 0 and 1. 1 and what? 1 and third. 2 and what? 2 and 1/9. -1 and 3. -2 and what? 9. Connect these points, connect them, and you will have a graph like this. This is the graph of third to the power x. What do you notice about this graph and the previous one?
Reflection about
The blue graph is just the reflection of the original graph about the line, about the y-axis, about the line x equals 0. So why is that? Yes.
This one will be 3 to the power of -x.
Excellent. In fact, if you look at third to the power x, it is 1/3 to the power x. It is 3 to the power -x. It is just the same as the value of the function, but replacing x by negative. And this is the case when we have reflection in the y-axis. When we replace x by negative x, we have reflection. So in fact, it is better to think wherever you have a function like this, think about it like 3 to the power -x. It will be much easier. And it will be the same as the graph of 3 to the power x reflected in the y-axis. Excellent. Now, what is good about exponential functions, ya shabab, that they are like Chinese people. All of them look like each other, okay? They have the same feature, almost the same properties. Look at, where is our function? Here it is, 3 to the power x. Here it is. Look, this is 2 to the power x. This is 5 to the power x, 10 to the power x. Now here, when we have the base half, or in other words, when we have 2 to the power -x, 3 to the power -x, 5 to the power -x, 10 to the power -x. What you can say? Do you have a word to say about this family of exponential functions? Yes, please.
They intersect the y at the same time.
All of them passing through the point 0 and this is the first remarkable point. Yes. Why? Do you know why? Yes. Yes, please.
power to the power to 0 is always 1.
A to the power 0 is always for any a greater than 0 and not 1. You're right. So in fact, because a to the power 0 is 1, all of them will pass through this point. What else? Please give me your remarks about these graphs, please. Yes. Yes, please.
They do not intersect the x-axis.
So you're right. X-axis is a horizontal asymptote. They will never ever intersect this line. I'm talking about a to the power x. Yes, again, what else? Yes, we did that. We said that. All of them passing through the point, all these graphs pass through the point 0 and 1. What else? They are continuous functions. Excellent. Yes. Excellent, Ya Abdul Aziz. Yes, excellent. Very nice remark. When a is greater than, look here, when a is greater than 1, you have 2 to the power x, 3 to the power, they are what? Increasing. But when a is less between 0 and 1, they are what? Decreasing. Very nice remark. What about the range? No one noticed something about the range and the domain? What is the domain of each one of them? All the real numbers. But the range is what? Only the positive number from 0 to infinity. The summary of properties of these functions is here. And it is worth mentioning here that the x-axis is the horizontal asymptote. Why? Because when x goes to negative infinity, it approaches 0 here. Look, here in the case of a between 0 and 1, it approaches 0 when x goes to infinity. All of them passing through the point 0 and 1, and also 1 and a. When x is 1, the function will be, the y will be a. When x is negative 1, it will be 1 over a. Now, do you know who is this person is? Who is this person? Who is this function? Now, this is the benefit of the graph. When you see the picture of someone, oh, I know him. He is. He gave you a hint here. He said that this is a to the power x. Just you need to know what is a. So here, what is a? Clearly, a is greater than 1. Is that right? Because the graph is increasing. Here, clearly, it is less than 1, and of course, greater than 0, because it is decreasing. Now, here, how to find a exactly? What is it? You will use the given point. So what do you have here? You have a to the power what? 2 equals 25. This is x and this is y. This is x, this is y. So a to the power 2 equals 25. What is a? Why not negative 5? A cannot be. A is always greater than 0. It cannot be negative. Excellent. What about this? We have a point here that can help us. Here we have what? A to the power 3 equals to 1 over 8, right? So what is a? You will just take the cubic root of both sides. You will get a half. A is a half. So the function here is a half to the power x, which can be written as 2 to the power negative x. And here it is what? A to the power, which is what? 5. Here it is 5 to the power x. You need to remember the properties of transformations of functions, or in other words, the graphing techniques. This is shifting what? Up, down, right, left, reflection in the, and this is stretching and shrinking. It depends, vertically or horizontally, or depends on C, if it is greater than 1, less than 1. Now, how to sketch the graph of 1 plus 2 to the power x? It is just 2x to the power x to the power plus 1. So it will be 2 to the power x shifted what? 1 unit up. So you will start with the graph of 2 to the power x. This is the graph of y equals 2 to the power x. You will shift it up. So what you will do? Are you going to shift all the points one by one? No. You will just focus on this main or key point. This point is what? 0 and 1. It will become what? It will become 0 and 2. So the graph will be, all the points will be going up. Also, there is something that will go up also. The horizontal asymptote, what it was? The x-axis. Now it will be what? Y equals 1. Y equals 1 will be the horizontal asymptote. Let me show you the graph.
Why exactly?
Everything will be shifted now. When x goes to infinity, you will see what? You can make the same values that we have. Look, forget about this graph. We use it just as a helper. Now remove this graph. Now this graph, what will be? When x is 0, what it will be? 2. When x is 0, it will be 2. When x is negative 1, negative 2, it will be never ever be less than 1, because this is the 1. This will be, of course, the smaller number. When x goes to infinity, it will approach 0. Now, what also changed? Not only the horizontal asymptote. What? The range also. Now the range is from where to where? From 1 to infinity. And this is very interesting. When we have vertical shift, by 1, the range will start from 1, and so on. We will generalize that later. What else? Also, the horizontal asymptote is y equals to 1. And of course, the range is still the same, all the real numbers. What about this one? H of x equals to negative x, negative 2 to the power x. It is the same as the graph of 2 to the power x shifted in the or the y-axis. Please, is it reflection in the x-axis or the y-axis? In the x-axis. Please revise the techniques, the slides that I told you about. Here it is. So in fact, here y it is 2 to the power x. It will become y equals negative 2 to the power x. So here it is totally positive. Here it will be totally negative. So it will be below the x-axis. So this is the graph of the function negative 2 to the power x. And you can see clearly here that the range is from where to where? From negative infinity to 0. The horizontal asymptote is still the same. The domain is the same. What about 2 to the power x minus 1? It will be the same as the graph of 2 to the power x shifted horizontally. 1 unit to the right. So it was here like this. Where it will be? This is 0 and 1. So this point, it will be where? It will be 1 and it will be here. So the graph will be like this. Here it is. Do you notice something also? You can think about it in a different way. 2 to the power x minus 1, it is just 2 to the power x multiplied by 2 to the power negative 1. Is that right? So this is in fact a half multiplied by 2 to the power x. So it is the same as the graph of the function 2 to the power x multiplied by a half. And this is what? This is vertical shrinking. So it has been shrunk vertically by half. So every y value will be divided by 2 or multiplied by half. Look here, it was 1, now it becomes what? A half. It was here 2, it becomes now what? 1. So these two transformations here are equivalent to each other. In this case only, they are not always the same, but for this specific function, they are the same. The domain is the same, the range is the same, the horizontal asymptote is the same. To summarize this, we will summarize here the horizontal shift and the vertical shift together. Look, when you have a to the power x, when you have horizontal shift here, and this is vertical shift, what will happen? The domain is still all the real numbers. The range will be what? C to infinity. What is C? The vertical shift. And the horizontal asymptote, y equal C, the vertical shift. Now, if you have reflection in the x-axis, what will be the change? Only the range. The other will stay the same. Just it will be below the x-axis instead of above the x-axis. What about if you have reflection in the x-axis? This is another case when you have a to the power negative x, and it will be reflection of a to the power x in the right in the y-axis. You can of course apply the same ideas for such function. Okay, now it is time. I think unfortunately we don't have much time. We will go to 4.2, the natural exponential function. It doesn't mean that what was before it was not natural. In fact, it was. But this is in fact just to distinguish between it and between the other exponential function. This function, it is a special function. It is about the number e. What is the number e? It is this irrational number. And of course, this number, I will skip the details. I brought here some links for you if you are interested about the story of this number. What is this number really, from where it comes, and why it is so special? By the way, the letter E is the first letter from the name of the mathematician Euler. So they call it the Euler number. In some textbook, they call it Napier number. Even in the Arabic book, I have read some books, they call it Al-Adad al-Naybiri, نسبة إلى Napier, the one who discovered the logarithmic functions. But of course, not Napier or Euler, none of them he discovered this the number. The one who discovered this number is Bernoulli, well-known mathematician. He discovered this number, in fact, when he was working on the compound interest. You know the compound interest in banks, الربح المركب. In fact, it is shortly, again, if you want, the details are here in these links. But in fact, you can just think about it as a limit. When n goes to infinity, look what will happen here. This is in fact 1 plus 1 over n all to the power n. This is represent that the rate of interest or the compound interest is 1. This is the period, how many over a month or a year or whatever. So look here, when you have here, when n goes bigger and bigger and bigger, the value of this, the limit is approaching specific number. And you will study this in Math 101, that the limit when n goes to infinity, it is e equals to this specific number, which is 2.71828 and so on. Of course, it is irrational number. It cannot be written as a ratio of two integers. Also in Math 102, you will study that this is just this series. It is just a summation of 1/0 factorial plus 1/1 factorial plus 1/2 factorial and so on. It is an amazing number. It is like pi. These يا شباب numbers e and pi and 0 and 1 and I. These are the most famous, well-known numbers in mathematics. They are combined, by the way, interestingly, they are combined in one equation. It is called Euler equation. It is like the Einstein equation, E equal mc squared in physics. In math, we have this equation. It is an amazing. Remember that you will see it in the future, inshallah, when you study advanced courses. This equation has the 5 numbers, E, I, pi, 1, and 0. You cannot find any mathematical text without one of these 5 numbers. It is not easy. Okay, now this number, again, what I want you to remember, just that E approximately it is 2.7 shortly to make it easier. So now when we have e to the power x, which means that all of this number to the power x, what do you think it will be? The graph of it will be what? Similar to the graph of what? Close to the graph of 3 to the power x, because it is 2 to the power, almost 2 to the power 7 all to the power 3. Approximately, it is not the same. I'm not talking about it exactly. So this is the graph of this function, e to the power x. So when you have e to the power x, it is like others, but of course it is called natural. This is the reflection in the y-axis, the reflection in the x-axis, and the y-axis, and this is the reflection in the x-axis only. You will love this function, Ashba, because what is special about this function? This function, you will see that in Math 101, that the derivative of this function is itself. When you differentiate this function, you will get the same function. When you integrate it also, the integral of this function is the same. Its integral is itself again. So this is why it will be one of the most functions that you will like when you study calculus. This is the summary of section 4.1 and 4.2 together. I think I should spend with you like 1 minute to solve this interesting exercise. So let's make it a little bit interesting by, you know how to sketch the graph of a to the power x. So easy, when a is greater than 1, right? Now, what about when you have your lovely function, the absolute value? What you will do? Yes. It is always only positive. A to the power x is always only positive. You need to deal with this function. All what you need to do to ask yourself, what is the absolute value of x? The absolute value of x, it is either x or negative. It is x if x is non-negative. It is x if x is negative. Use this fact here. So this, the absolute value of x will be x or negative x. Now, what you will do, forget about this. Just focus on this. What you will do, you will sketch the graph of what? A to the power x, here it is. This is a to the power x. And this is a to the power negative x, right? Now you will take a to the power x if x is greater than or equal 0. When x is greater than or equal 0, you will take this part. This is 0. This is x greater than or equal 0. So you will not take this part. When x is less than 0, this is x less than 0. You will take what? A to the power negative x. You will take this part. You will not take this part, just the upper part here, this one. Here it is. And this is the graph that we are talking about. Now, what you can notice about the domain and the range. The domain is all the real numbers. The range from 1 closed to what? To infinity. What about the horizontal asymptote? No horizontal asymptote, because when x goes to infinity or negative infinity, the function goes to infinity. And there is no, it doesn't approach a specific number. Let's go to this. What will be the difference when you have a to the power negative, the absolute value of x? The difference here, that what? That here it will be here a to the power negative x and here a to the power x. So what you will do here, this is the graph of e to the power negative x. You will take it when x greater than what? You will take this part. This part you will not take it. Now, when x is less than 0, this is the graph of a to the power x. You will take the, when it is less than 0, you will take this part, not that part. And this is the graph that you will have. Look. Amazing. What is the range? This kind of strange. From 0 open to 1 closed. And what is the horizontal asymptote? The x-axis. And the domain, of course, is all the real numbers. We are done. We will stop here and continue next class, inshallah.